Welcome everybody to the first today's scientific session, which will be about galaxies, active and passive. And our first speaker today is Reinhard Genzel, who will tell us about 40 years journey, presumably to the Nobel Prize. So welcome and
thank you very much, Agnesia. Yes, what I was hoping to do is to tell you about progress we have made in a fairly large team in testing the massive black hole paradigm, and in particular doing this in the center of our Milky Way. Mainly because, of course, the Milky Way is the closest galaxy. And as you will see, this is a bit like a Russian doll. There is a big doll, that's general relativity. We'll start off with that. And the prediction of black holes. And then, of course, we come to further dolls, namely parts of the project, which in my case really have taken 40 years to get from where we started and to where we are now. And so this is a fairly major program, has involved many people, young people, and not so young people, mainly in Europe and here at the Max Planck Institute for Extraterrestrial Physics, as well as Cologne University, another Max Planck Institute in Heidelberg, two observatories in Paris, and Grenoble in France, and the University of Lisbon as the key parts of what we call the gravity collaboration. And I'll tell you more about that. Now, as a backdrop, let's just recall that a little over 100 years, of course, Albert Einstein presented his theory of general relativity in Berlin. And already 1 year later, Karl Schwarzschild, there on the top in this picture, provided the first solution of the spherically symmetric distribution, which had in it one of the crucial predictions of new predictions of general relativity, namely that mass distributions, if sufficiently compact, have such strong gravity that even light cannot escape, and therefore you have a region within the so-called event horizon, which does not communicate anymore with the world outside. So that was the birth of the black hole. It wasn't called that at that time, but certainly that was sort of the point when theoretically this was a new thing. Now it took 50 years really by the theorists, many very famous people. I've just shown a few, in particular Roy Kerr, who's found a solution of a rotating system, and then Roger Penrose, who actually, together with me and Andrea Ghez, got the Nobel Prize in Physics last year. And Roger put this all in a very generalized setting. And then others like Stephen Hawking, etc., were looking, of course, toward parts of the theory which we still don't have fully understood, namely the smaller scales, the singularity, the prediction of a singularity of mass at the center of a black hole, and the question of information. I won't talk about these, but just basically say that, you know, it took also 50 years before astronomy was able to get into the game and identify some candidates which might be such objects. And the first ones actually were X-ray binary sources, which the X-ray astronomers, Riccardo Giacconi and others, discovered, and we now think are systems with a stellar black hole. I won't talk about those either, but I'll talk about the more massive variety of black holes which came in to the observed realm with the quasars. The radio astronomers had discovered very bright radio sources, which on optical plates were looking like dim stars, but in their spectra showed clearly redshifted emission lines, which were, a signature of a very substantial distance from the expansion of the universe. And a number of theorists working on the problem in the 60s then predicted that these bright sources, which, if you correct for the distance, are 1,000 times or even up to 1,000,000 times the luminosity of the entire Milky Way, that these sources might be accreting massive black holes, so objects with millions to billions of solar masses, and basically gas and stars accreting in a disk-like configuration towards the black hole, and before the gas and the stars would disappear behind the event horizon, could convert the energy due to gravity into heat and radiation in an efficiency which is remarkable, 100 times that of fusion from hydrogen to helium in stars. So that was the birth of the paradigm. Of course, the question is, how would you prove it? The best way to prove that there is a mass concentration, of course, is that you use the effects of gravity itself onto the environment surrounding it. And in fact, Lindenbell and Rees wrote a very famous paper in 1971, where they basically said, well, maybe these bright quasars are just one species, if you like, the active species of such accreting black holes, whilst most others might not be actively accreting and therefore are not easily seen. And if every galaxy would have such a massive black holes, maybe even our own galaxy might have one. And then one could look into the galactic center and also nearby galaxies, of course, and look whether there were massive concentrations by the action of gravity of such a massive black hole into the environment. Look at the motions of gas, look at the motions of stars. So that was the proposal by Lindenbell and Rees. Now, it did take about 10 years, I would say, before the observers really got into gear and found, the first evidence. And I'll tell you a little more about that as we go on. Now, let's move from that time another 50 years forward to now, and we find ourselves, after this longish period, in just a plethora of fantastic evidence in favor of this black hole paradigm. One which is the subject of my talk is the using stars in particular and ever higher and sharper images and spectroscopy in the center of our Milky Way to pinpoint and then also constrain the nature of the central mass in the galactic center, which, as you will see, is a compact radio source called Sagittarius A star. Now, another fantastic discovery over the last few years, of course, is the discovery of gravitational waves from inspiraling and merging stellar black holes. And the first one, which was found right away, proved that this is likely indeed such a system where two stellar black holes in spiral then emit gravitational waves and in the end form a single stellar black hole. Finally, the radio astronomers have been using intercontinental radio interferometry, VLBI, at very short wavelengths, 1 millimeter wavelengths, across the entire globe to realize resolutions which were previously unheard of only about 20 micro-arc seconds. 20 micro-arc seconds is about 10 centimeters on the moon. So that's a fantastic resolution. And if you then look at nearby active galaxies like M87 in Virgo, then you see the center of what is known to be an active nucleus with radio jets and so forth. And in the center of that, there appears to be an object which has a central darkish region, which is what, in fact, general relativity would predict. for the effects of photons by the black hole, namely that the photons cannot escape from the central region, are bent, and even fall into the black hole. So after 100 years, we are for the first time in a situation that we have quantitative evidence, black hole paradigm, and it's a very fun, really outstandingly interesting story, which is not yet finished, as you will see when we come to the end of the talk. Now, Lindenberg and Ries, as I said, propose that one looks at the nearest galaxy, the galactic center, which is only 27,000 light years away, a factor of 10 to the 4 times closer to the nearest quasars. The disadvantage of the galactic center, however, is that as you look from us to the galactic center, the light has to go through the entire Milky Way, and interstellar dust particles absorb the light, the optical light, almost completely, so that you have to go to longer wavelengths, radio wavelengths, infrared wavelengths, and or shorter wavelengths, X-rays, gamma rays. So that was initially not possible because just the technology wasn't there to image and inspect and do spectroscopy in the infrared. But nowadays we can do that, and I'll say more about the importance of technology in a second. And what you see here is the central few light years at the center of our Milky Way in infrared light in 3 different colors. And what you see is the stars, the central star cluster, extremely dense, about 1 million times denser than the solar neighborhood here. And in fact, surprisingly active. The objects you see here are by no means solar type stars. The blue ones are up to 100 solar mass Wolf-Rayet stars and O stars, also B stars. The red objects are various type of Wolf-Rayet stars and giants, cool giants. So galactic center actually is a surprisingly active region, because if there would be a massive black hole here, theory would tell you that it's actually not possible, or at least not easily possible, to form stars. Yet apparently that is happening here. And in fact, when that evidence came to the fore, many people, including in fact Martin Rees, started saying, well, maybe there is no black hole here after all. So that puzzle has accompanied us as we were making progress in looking at the central region. Now, how would you then look for a black hole here? Well, there is not only stars, but of course there's also radio emission. And in the center here, the radio astronomers found a very compact radio source. We now know for millimeter VLBI that this radio source has a size of about 40 microarc seconds. We don't have an image quite yet for technical reasons, which I don't have time to discuss, hope to have it soon. But this very compact radio source is likely, so to speak, the central region. That's sort of the spot marked X, where you might suspect a massive black hole to be located in the middle of the star cluster. And surrounding this region is ionized and neutral gas in addition to the stars. So in this picture, the blue are the stars, the pink color is ionized gas, ionized by the hot stars, and the green is neutral gas, which is swirling around as streamers in the central region. And if you take spectroscopy in the infrared, then you can look at the Doppler motions of this gas. Now, Charles Townes, Nobel laureate for the invention of the laser, in his later years started to do astronomy in Berkeley with his students, and he was a pioneer in infrared spectroscopy. So he and his students, and then I joined, in fact, his group, initially as a postdoc, but later on as a colleague on the faculty, used this infrared spectroscopy to map out the motions of these gas streamers. And we found that the motions are very large, hundreds of kilometers per second on scales of a parsec or so. So if you're on the left side, interpret these motions in terms of gravity, then you can construct what you might want to call the mass distribution as a function of distance from the Sagittarius star on the horizontal axis in logarithmic units. And what you see is on large scales, of course, the mass increases. That's just because you're looking at the distributed mass from the stars themselves. Then you come inwards, and within about 1 parsec or so, which is the region you see on the right, then all of a sudden the motions increase, or the mass stays more or less constant at a few million solar masses. So if these gas motions really represent gravity, we felt there was the first evidence that there is an object here of a few million solar mass, which is larger than what you could explain just solely by the stars. So that was the first evidence in the 1980s. Unfortunately, not everyone believed us, because many people felt that gas is a poor tracer of gravity. You can, after all, expect that there will be magnetic fields in this region, and they are. And the magnetic fields would interact with the ionized gas very strongly. There's these stars, which are O stars and Wolf-Rayet stars, which have winds. They might push around that gas. So the tracer gas, ionized gas, is not very good, not very safe. Also, the distance of a few light years or 1 parsec is very, very far away from the event horizon of a few million solar mass black hole, about 1 million times that event horizon scale. So, it could be other things other than a black hole, which is in here. You might think of a concentration of very weak stars or neutron stars, which basically formed most of that mass. So clearly, by the 80s, we knew there was something, but we knew we had to go inwards. We had to use stars instead of gas, and we had to go and have higher resolution. So that meant new technology, because the infrared, as you know, has been something which is much more difficult. And we didn't initially have low noise infrared imaging detectors. That came about through the American military, actually, initially, and then the Hubble Space Telescope. And by the early 90s, I had then moved to Munich and formed here a new group at the Max Planck Institute. We started building cameras and spectrometers. We then also realized that one of the problems making images in the galactic center is the problem of seeing. You all, if you have ever observed in the visible, then of course you know that the atmosphere refracts and distorts the images from a distant star and makes the images very unsharp. Now, of course, you go to space, but a 2-meter telescope like HST doesn't have very high angular resolution. And the solution nowadays is adaptive optics. You basically analyze the wavefront, and then you have a deformable mirror, and you bend the wavefront straight, and then you get sharp images. I don't have time to get into this too long, but clearly with that kind of technology, then you can make telescopes nowadays of 10 meters diffraction limited with a resolution of about 50 milliarcseconds, 10 times better than the seeing limited resolution. Now for that, you need a star which is bright enough to make the analysis. Not always do you have such a star, and therefore we've learned to also develop artificial laser guide star systems where we shoot lasers in the sky, focus them at altitude of about 90 kilometers, where there is a layer of sodium coming down from the atmosphere, outer atmosphere. When meteorites enter the atmosphere, get destroyed, and sort of a little rain of material has sodium atoms in them. We focus the beam there, and that makes resonant backscattering, which we can then use as an artificial star. So as you see, just in this short discussion, the combination of big telescopes on the ground, of low noise infrared detectors, laser guide stars, adaptive optics, and of course, modern computers and so forth, really was the path we had to go in order to make progress. And then progress came pretty quickly in the years to follow. At that time, another team had entered the scene, Andrea Ghez and her colleagues, Mark Morris, Eric Becklin, and others at the University of California, Los Angeles, using the Keck telescope, the new big 10-meter class telescope on Mauna Kea. We were using the ESO telescopes in Chile. At the time when we started in the 90s, that was not yet the VLT, that was the NTT, which is nowadays a modest 3.5 meter telescope. But the idea was the same for both groups. You would take sharp images, initially with speckle and then with adaptive optics. Then you would take another sharp image a year later, another sharp image, etc. And then over time, you would hope to see a motion. And indeed, in this picture here, I've overlaid 3 different years in 3 different colors in the mid-90s. The cross, the green yellow cross is Sagittarius A star, that radio source. The circle is a light month. Okay, so that's already pretty compact region. And then you see that there's a star very close to Sagittarius star, which clearly is moving in these 3 different years by about 2,000 kilometers per second. That's 100 times the Earth around the sun. So if you again use Newton, V squared R over G, then your mass, which you would infer from that motion, is several million solar masses. So this observation by itself immediately tells you that the same few million solar masses which we had seen on a scale of a few light years with the gas motions, you can see in the stars on much smaller scale, a few arc seconds away from the central point source. And it's concentrated because look, if you go out from the center, then the color, the prism effects get smaller. So the outer stars here look like white, meaning they're not moving as fast. And that's exactly what Kepler's laws would tell you, right? That as you go away from a central mass, which dominates the motions of the stars surrounding them, then the velocity should go down like 1/3 of the distance. And indeed, that's what you're seeing. So by the mid-90s, both groups came to the conclusion that indeed, there's a few million solar mass object in the center. It's likely associated with the radio point source. And we are now on scales which are further in, but still about 100,000 times the event horizon size. So how could you do better? How could you do better? Well, you needed to go still further in, and you want to measure more than just motions. You would, at best, actually see the full orbits of stars. But that was not obviously possible. In astronomy, that's rare, that you can see motions outside of the solar system. But here, nature gave us stars which are coming so close to the central point source that they are actually giving us orbital sections and even full orbits. So a few years later already, we had the first star going through a Perry approach around Sagittarius star. That's the star S2 or S02. And as you see down there is Sagittarius star, and the blue data are the ones from our group, and the red data are from Keck. Very good agreement. And in 2002, that star came as close as 17 light hours. 17 light hours, and it moved at that time with about almost 3% the speed of light. So that tells you that the mass, indeed, that few million solar masses must be concentrated within that Perry approach. And that is already now about 1,000 Schwarzschild radii. So we are really come a long way, and it's a beautiful ellipse, highly elliptical orbit, which you can precisely measure and really get good quality information to it. So by 2002, both groups publishing within a few months of each other came out with that information, and I think convinced most astronomers that indeed this is the best evidence for a massive black hole. But let me ask the same question again. Must it be a black hole? As scientists, we need to exclude other options. It's not likely that there is a neutron star cluster which could hide in there, but how can we do better? And also, in order to make the conclusions which I just gave you, we use general relativity. We assume that general relativity is correct on these scales. So by the mid-2000s, we knew this star would come back in about 16 years, in 2018. And we felt, well, if we make instruments which have still better resolution, then we might, at the next Parry approach in 2018, actually go ahead and use this as a laboratory to test general relativity. So how could you do that? Well, I'll tell you the story. It has to do with interferometry. In the meantime, both groups collected data on not just one star, but about 50 stars. So by 2015, both groups had about 15 stellar orbits, or partial orbits, I should say, all of which gave the same information, the star S2 being the best one, but the others gave the same answer, namely a few million solar masses. So that's a beautiful, beautiful confirmation. Now, one of the problems here is, how did these stars get here? These are stars which are actually fairly young. How did they get to the center? If you calculate the equilibrium time to move into the center, then you're talking about billions of years. These stars are only 10 million years of age. So that's a puzzle, actually. But let's be happy. Nature gave us these stars as test particles for the gravitational potential. Okay, so the next step for us was higher resolution. So far, we had been measuring with one of the VLTs, namely the right there, 8-meter telescopes of ESO on Paranal Mountain in Chile. But of course, I grew up in radio astronomy, and I was very familiar with interferometry. So I hit on the idea, hey, let's just build an instrument which actually effectively combines the light of all the 4 VLTs to a single telescope of effective diameter 130 meters. So that gives you a resolution which is still a factor 15, 20 better than what we get with a single telescope. So milli-arc-second resolution. So we set out under the leadership of Frank Eisenhower in this consortium, which I've already described to you. And over the next 10 years, we built Gravity, which is a very, very complex instrument. I don't have time to get into it, where the light is combined underneath this platform in a tunnel, and then in a cryogenic box, which you see there on the left, is analyzed, and the fringes are detected, etc., of all the combinations of the 4 telescopes. So that gives you 6 baselines, and then you use Earth rotation aperture synthesis to make images. Very challenging undertaking. It's about 100,000 times more difficult than radio astronomy, just because wavelengths are short and the coherence time of the atmosphere is a millisecond. So you have to do all the corrections on kilohertz scales. The vibrations have to be eliminated, et cetera, et cetera. So it's a very, very complex undertaking, but it did work. It did work. It does work, and it gives us fantastic information. Gravity basically gives us the resolution of a Eurocent coin on the moon in terms of astrometric precision. That's 10 micro-arc seconds. That's exactly the event horizon scale of a million solar mass object. So when you look what happened over time here in this setting on the right, you have 4 panels there. Then we started in the 1980s, early 90s, with seeing limited information on modest sized telescopes. So you see stars, but they're smeared. The next big step, as I explained to you, we used speckle imaging and then adaptive optics to improve the resolution by about a factor of 10. Now you see individual stars very clearly. Also, you get much fainter stars because, of course, the bright stars now are shrinking together because of the resolution. And you see the black hole itself in the center of this. Now then, with gravity, you can now pick out the central region there and make an image of that. And in fact, this is an image from this year, from May, end of May this year, when we looked at the galactic center with gravity. And you see, wow, there's not just one star there. There's a whole bunch of them. So the interferometry we now have is so sensitive that we can actually see the whole environment on scales of about 1,000 Schwarzschild radii. And so we see, in fact, as you see several stars, and if you observe from night to night and from month to month, you see them moving, which is shown in the left bottom picture. There's one star, the star S29, which happens this year to have made another Parry approach, very much like S2, with about 3% speed of light and fantastic information on the gravitational potential. So that's the progress you can get with these high resolution interferometric techniques. So let me then summarize for you what we have found. So we started off with these orbits, which you've seen, which come from the collection over about 15 years, which both groups did. Now we have this year seen 3-4 stars, which come very close. And so we can analyze the inner motions with gravity with high precisions. We are looking at several of the stars simultaneously. S2, of course, is now already on its way back out, but we can expect to see every year several stars going through very close Parry, which begs the question whether there might be stellar collisions here in the center at some point. And indeed, the possible timescale of such interactions is only a few thousand years. So this is a fantastic astrophysical system in addition to the whole question of the black hole itself. Now, we can, as I said, we can measure the motions from day to day with high precision, so several tens of micro arc seconds, and then derive the properties of the orbits, the orbital parameters, as well as the properties of the potential, the mass. We can also measure the distance to the galactic center with extremely high precision, as you will see, a fraction of a percent. And this is the way to then see the effects of general relativity. The first one is the gravitational redshift. Basically, the fact that when you have light being emitted near a large mass, then it's affected by gravity. The clocks are going slower in a region with a lot of gravity. And basically, on the right side, if you look at the spectral properties of S2, then you see the large excursions due to the motion of the star. The Parry in 2018 was near the peak there at 4,000 kilometers per second. But that's just the total orbital motion. If you subtract the Newtonian part from that and just look at the part which is the residual part, then you see general relativity itself. So Newton is now a gray line, horizontal gray line, and the prediction by general relativity is the red line. And you see the data, of course, cyan data points agree extremely well with general relativity. So it's very clear that that test has been passed. Now, the next effect which you can see is the so-called Schwarzschild Procession. As you know that in Newton, if you have a constant mass in the center and another object bound orbiting around it, it would be on an ellipse which stays constant in space. Not so in general relativity. In general relativity, there's an in-plane prograde precession called Schwarzschild Procession, even if the black hole is not rotating. And in the case of S2, that precession is about 12 arc minutes per 16-year orbit. And we can see that, again, as a measure in the residuals. Look on the right side. The Apo, the last Apo position are these red data points. And then Parry is when all of a sudden in 2018, the data deviate from the gray Newton orbit and follow the red GR orbit very clearly. This is sort of like a kink. The precession is not continuous in this case because the orbit is so elliptical. You can see also the precession by comparing in the upper right the data from 2004 near Apo. These are the open blue circles with the gravity data points from this year, 16 years later, and you can clearly see the shift of the entire orbit to the right. That's exactly what Schwarzschild Procession would predict. Another thing you can look at right away, at least qualitative, that's obvious to you, you can make a statement about what other masses there might be here. Because this Schwarzschild Procession effect is only clean if there's not a disturbing additional source of mass. If there's an extended mass, you would not see the Schwarzschild Procession as clearly. And I'll come back to that in a second, because that gives us information on objects near the black hole. Finally, we see the black hole itself. I mentioned that already. And from time to time, the infrared lights up. The radio, of course, is more like a stationary emission, but both can be used to constrain the mass in the very center. The flares in the infrared show up as little light spots, which then move. And for about 30, 40 minutes, basically, there is a bright source which moves on scales of about 10 times the event horizon size and speed of about 30% speed of light. If you analyze that, that is another direct confirmation that the few million solar mass you have derived from the orbits of the stars now very precisely must be contained within a few times the event horizon size. So that really is, I would say, very good evidence for a black hole. Now you could ask again the same question, must it be a black hole? It's consistent with a black hole. It's some of the best evidence now we have, and certainly the best evidence for massive black holes, but we still haven't seen the spin of the black hole. So we would like to measure the spin of the black hole by perhaps seeing so-called lens steering precession of a star, which is still closer than the star S2. But the progress has been enormous, and we can now actually map out the mass distribution in the galactic center with high precision. So when we started 40 years ago, in the left diagram, we were there on the right where you see the star cluster turning over into a constant mass. Then with the VLT, we were beginning to see these innermost stars, in particular the star S2, and these flares, which I just described, now going all the way in to a few times the event horizon size, just outside of the black hole itself. And throughout this entire region, this really looks like a single mass. In fact, if you look on the right side, that's the current best evidence we have of the mass distribution right around the black hole. And all evidence is that there is hardly any additional mass other than the central point mass out to about 3 or 4 times the upper distance of S2. Only if you go out further, then you're beginning to see the extended mass of the star cluster, which is coming in then at larger distances. So that's interesting because that tells us this is a single black hole. This is not, a binary, for instance. And if there are lots of stellar black holes in this region, then they cannot really contribute all that much to the mass within the peri-distance of the star S2. So it's a very, very interesting, sharp delineation of the mass distribution. Also, we can exclude any contribution by dark matter. That's been speculated by a number of people that maybe you could have a dark matter spike near a black hole. If there is such a spike, it does not contribute more than, say, 0.1% or less to the mass within the S2 orbit. So this does really look like a black hole. As I said, we measure the mass to now a fraction of a percent, likewise the distance to the galactic center. We've seen with good confidence several effects of general relativity. We also test the equivalence principle. So it really does look very good. And the future is planned out as well, as I mentioned. If we get to see the lens steering precession, we can measure the spin. If we have the spin, then we can go to the next and last step, which is to test the no-hair theorem. The no-hair theorem is basically the statement made by general relativity that if you have a spinning black hole, then the spin A and the mass M are the only two quantities you need. Everything else is determined, all multipole moments of the distribution. So for instance, the quadrupole moment Q is determined by a combination of M and A. And this nuisance parameter epsilon, which has no units, is 0 in general relativity. The current measurements we have constrained epsilon to be somewhat less than 1. The gravitational measurements of LIGO also are in the same kind of regime. As we look into the future, if we combine gravity measurements with measurements of the Event Horizon Telescope with the radio measurements, we might push that to 0.1. And 20 years from now, my wager is that the ESA space mission, LISA, which is going to do gravitational waves around massive black holes, might finally settle all of this and test general relativity on a scale of less than 1% and really settle the issue. So we've made enormous progress over the last 20 years to verify the massive black hole paradigm in the galactic center. I think we've done it very well. Other galaxies, I'm sure, will follow, and the LISA mission should be sort of the crowning of all of this. Thank you very much for your attention.